Hello everyone. In this lecture we will be learning about CMOS transistors and the theory of it in details. In all the earlier lectures we have treated transistors as ideal switches. That is, if we consider this NMOS, if we put a gate voltage VG over here, the NMOS turns off and current flows through it. If the VG is equal to 0, then NMOS turns off and no current flows through it. This is simplistic model, ideal model of a switch, but in reality when we use MOSFET there are other factors which come into effect. Only non-ideal factor we have considered is NMOS. We have considered NMOS passes one poorly and PMOS passes 0 poorly. This is a non-ideal factor that we have considered. In this lecture we will be considering lots of other non-ideal factors. Now the question is from where do those non-ideal factors come? Generally, if we consider these MOSFETs as ideal switch, it can take any amount of current. But in general, in case of real MOSFETs, the amount of current passing through them is finite, and it depends on different parameters of MOSFETs. It depends on the terminal voltages and the current voltage relationships of the MOSFET. Again, there is a delay involved in it. Why is a delay there? Because there is capacitance in MOSFETs. We'll be learning about capacitance in this lecture. If there are capacitance, we know I is equal to C dV dt. We know this equation, or I is equal to C del V del T. It brings a delay of del T, which is C by I del V. This delay is caused by the capacitance, which is finite in amount, and as we can see from the expression, the lower the capacitance, the lower the delay, and we want the delay to be 0 or as low as possible. But that is actually not 0. So this is also a non-ideal component which we need to consider. And we'll be learning from where these non-ideal components come and what are the design rules that must be followed in order to decrease the non-ideal components. Now, firstly, important factor is MOS capacitors. MOS capacitors, this is a MOSFET. We are considering this is the gate. This is the insulator here, and this is the body. In this side there will be a drain, the drain part, and in this side there will be source part, which we are not considering at this moment. So firstly what happens is, suppose we have not put any voltage here, or we have applied a negative voltage at the gate. If we have applied a negative voltage at the gate, what happens is the gate becomes negatively charged, and the body, which is since we are considering NMOS operation, body is readily made of P substrate, and as a result there are plenty of holes in it, and the holes remain in the P substrate, and electrons remain in the gate. This method is this mode of operation is accumulation. Next, if we increase VG, that is the gate voltage, if we increase the gate voltage, what it does is it creates positive charge on the gate, metal gate, and this positive charge repel the positive charges or the holes of the p-type substrates, and as a result there is a depletion region created devoid of any charge in this place. This creation of this depletion region makes it operate at a depletion mode, and when we these things keep happening as long as the gate voltage is lower than a certain threshold voltage. When the gate voltage is more than that threshold voltage, then what happens? Then what happens is, this body is a p-type substrate, but there are minority electrons, minority carriers or electrons there. These electrons are attracted by this positive charge and get accumulated in the contact between the positive and negative charges. But these negative charges cannot cross this insulation layer and go to the positive charges because of the insulation provided here. As a result, there is a layer of electron created here, which is in the p-type substrate we get a region full of electrons, and we call this phenomena inversion, and this region of operation is called inversion region of operation. And when the inversion region has occurred, that is VG is greater than V threshold, then what happens is, we see here we have a positive plate, we have an insulator, and we have a negative plate. That is, this acts as a parallel plate capacitor. As a result, these configuration introduces capacitance in MOSFET operations. Now, terminal voltages are also important when we are bringing the calculations into consideration. We have three terminals: the gate terminal, source terminal, and drain terminal. So the voltage will be gate to source voltage, gate to drain voltage, and drain to source voltage. Gate to source voltage is Vg minus Vs, gate to drain is Vg minus Vd, and drain to source is Vd minus Vs, which can be written as Vgs minus Vgd. Now, the source and drain in case of a MOSFET is symmetric. That is, we can consider any one of the terminals as source and the other as drain. But when we apply this in the circuit, generally in case of NMOS, we consider that the source terminal is at a lower voltage than the drain terminal. So we always consider VDS is greater than equal to 1. Again, I am saying this is because of NMOS. We are considering everything for NMOS, and for PMOS everything will just be the opposite. And there is another terminal which we are not considering, the body. The body will always be grounded for our consideration. So, based on the terminal voltages, there are three modes of operation: cutoff, linear, and saturation. The cutoff mode. In the cutoff mode, the gate voltage or VGS is 0. And as we can see, the source is connected to the ground, so the gate voltage in its entirety is 0. When the gate voltage is 0, that is Vg is less than Vt, Vgs is less than Vt, what happens is there is no inversion region created. As a result, no current can flow from drain to source. Since no current can flow from drain to source, IDS is not created, and since no inversion region is created, there is no channel. As a result, the MOSFET acts as an off switch, or the MOSFET does not carry any current. This is called the cutoff region. Now, what happens when we increase the VGS? If we increase the VGS to a region to a value greater than the threshold voltage, what happens is there is an inversion layer of electrons created. Now, if we increase the VDS is equal to VGS minus VGD. Since VGS is increased, VDS will automatically be increased. If VDS is increased, what happens is here is a positive terminal and here we have negative terminal, and as a result, current flows from drain to source and electrons move from source to drain. As a result, a current flows to the MOSFET, and the value of the current keeps on increasing. As the value of VDS increases, the value of the current also increases. So the current directly is proportional to the voltage VDS. Now again, another thing happens is that as the VDS increases, if we keep the VGS constant, VGD must be decreased. That is, if this is kept constant, this must decrease. If this decreases, we can see that here the inversion layer will be thicker and here the inversion layer will be thinner, because the voltage applied here is more than the voltage applied here. And as we keep on increasing VDS, this region or this region of the inversion layer will go thinner and thinner, because the voltage applied here, VGT, will keep on decreasing. Now this phenomena of decreasing the voltage VGD creates a saturation region, brings about saturation region. How does it do that? If we increase VDS to a certain point, if we increase it very much, then what happens? VGD decreases by a lot. If VGD decreases by a lot, here in this region there is no inversion layer created, because VGD becomes less than VT. If VGD becomes less than VT, no inversion layer is created here, and as a result, the current passing through from drain to source no longer increases, and it attains a stable value, it attains a constant value. That is, the current saturates, and because of the saturation of the current, this region is called saturation region. And in the linear region, we have seen that the MOSFET works similar to a resistor. That is, the current decreases as the voltage increases. But in case of saturation region, it acts as a current source. That is, it gives a constant current. Now, another thing to bring into consideration is charge. The charge that a channel And why does a channel stores charge? Because of the capacitive arrangement. We have already learned about MOS capacitors in previous slides. Now, the current IDS, that is the current that moves from drain to source, depends on how much charge is in the channel and how fast the charge is moving. Now, before we go into how much charge is in the channel, we know Q is equal to CV. We have already learned this basic formula. Now, C is the gate capacitance. C is equal to CG. The gate capacitance is brought about by, we know capacitance is equal to epsilon A by D. This is a basic formula of capacitance. Now, epsilon is created, epsilon is created by the insulator, which is the oxide. So we write here epsilon oxide. Area is the width into length, and D is the thickness of the inversion layer, so small t. Now, epsilon OX by T is called oxide capacitance per unit area, or it is replaced by the term COX. So we get C is equal to COX WL. Again, we have to measure V. V is the gate voltage. Now, what will be the gate voltage? Firstly, we have to consider that the gate voltage will be the VGS that we apply minus the threshold voltage VT. Why have we subtracted the threshold voltage? Because the capacitance only work when there is an inversion layer. That is, here we have plus and here we have minus. At that point, it acts as a capacitance. So, in order to create the inversion layer, we have to apply a voltage greater than VT, and the effective voltage across the capacitance will be VGS minus VT. Now, another voltage plays its part, that is VDS. VDS is a voltage from drain to source, and here at this point the voltage is maximum, and at this point the voltage is minimum. And this channel charge we are considering for linear region, that is, the channel is acting as a resistor in this region. As a result, there is a constant voltage drop across the resistor. So we are let us consider a middle point in the channel. Here, the total voltage across a drain and source is VDS, and it keeps on decreasing as we move from the voltage keeps on decreasing as we move from drain to source, and at source the voltage is 0. As a result, at the middle point, we may consider that voltage is VDS by 2. That is the average of the total voltage. So we have to decrease these parameters as well. So this is the effective voltage across the capacitance that we have applied. So if that is the case, Q channel will be COX WL VGS minus VT minus VDS by 2. This value of Q channel will be required when we go on to actually measure the current that flows through. Now, another thing of importance is the carrier velocity. Here we see in N-channel MOSFET, the carrier is electron, and carrier velocity, we know the velocity is proportional to force. Here force being the electric field. So the electric field, lateral electric field, is the voltage divided by the length of the channel. So E is equal to VDS by L, and again carrier velocity should be proportional to electric field, as velocity is dependent on the force. So P is equal to mu E. Mu is the proportionality constant, which is called the mobility. It is a measure of how fast the carrier moves. In case of electrons, the mobility is high. If the carriers are whole, the mobility is lower. Now, since V is equal to mu E, we know V is equal to distance, velocity is equal to distance by time. In this case, the distance is the channel length divided by time. From that, we get T is equal to channel length by velocity. Now, we have replaced velocity by mu E from this expression, and again we have replaced E by VDS by L from this expression. So we get time is equal to L square divided by mu VDS. This value of time will be required when we measure the current. That's all for this lecture. In the next lecture, we will be deriving the IV current voltage relations of an NMOS and a PMOS. Thank you.